Hello students. In last lecture we have discussed about contents of electromagnetic waves and the sources of electromagnetic waves. Today we will study about the propagation of the waves. And in today's discussion we will consider uniform plane wave. Uniform means the magnitude of electric field and magnetic field are same at all points in the direction of propagation. So for that purpose, let us start from Maxwell's equation. And we have studied the Maxwell equations in differential and integral form. In differential form. Let us revise it. Here we have the first equation, del dot D is equal to the volume charge density, that is rho v. It is related to the Gauss law. And the second was, we can write 1, and the second was related to the non-existence of monopole, that was del dot B, it was equal to the 0, means monopole does not exist. And the third was related to the Faraday's law, that was the del cross E is equal to the del B over del T. And the fourth, that was related to the modified Ampere's law, that was del cross H is equal to the conductivity times E plus D. So we have these relationships in Maxwell's 4 equations in differential form. In today's discussion, we will try to solve Maxwell's equations and describe electromagnetic wave motion in different medium. And medium that we are going to consider, mediums. The first one that we will consider is free space. Free space means the space has conductivity 0 and the permittivity is termed as epsilon naught, and permeability for free space is termed as mu naught. So these are the characteristics of free space. Conductivity is the measure of ease at which an electric charge, or we can say heat, can pass through the material. And permittivity and permeability we have discussed in detail. So the first medium that we will consider, free space. The conductivity of the free space is 0. That it indicates that it does not allow the passage of charge or heat. The second medium that we are going to consider is lossless dielectrics. Dielectrics. And in case of lossless dielectrics as they are insulator, again the conductivity is 0 and the permittivity of the material changes to the relative value epsilon r times epsilon naught. Similarly, permeability also changes to permeability r mu r times mu naught. In this way, the lossless dielectrics are defined. Now the third medium that we are going to consider is lossy dielectrics. And in case of lossy dielectrics, the conductivity will not be zero, and as it is dielectrics, these two terms will remain like this. So in case of lossy, the changes occurs at this point. Now the conductivity is not equal to the 0. And the fourth medium that we are going to discuss is good conductor. And in case of good conductor, the conductivity is very high, and it is assumed that it is equivalent to the free space in case of permittivity. So that is epsilon naught, and permeability, it is differ from material to the material. Now out of these four, we will start our discussion from propagation of the waves in lossy dielectrics. Later we will find that these are special cases of that. So we will start from the wave propagation in lossy dielectrics. Lossy dielectric is a medium in which when an electromagnetic wave propagates, it loses its power due to poor conduction. So let us have some assumption. What are assumptions? For our discussion, the first assumption is the medium is linear. So we can say the dielectric medium is linear. Linear means the total electric field in the medium can be obtained by adding the electric field of the all waves traveling in the medium. That is the definition of linear. The first assumption is the dielectric medium is linear, and the second is isotropic. Isotropic means the value of epsilon and mu have same values in all directions, means they are scalars and they are independent of the directions. And the third assumptions that we are going to take is the medium is homogeneous. Homogeneous means the throughout the medium the value of sigma, permittivity and permeability are constant. So having these assumptions, we will start our discussion. And the dielectric medium is linear, isotropic and homogeneous. And the next assumption that we can have the medium is charge free. So overall we can say we have considered a linear, isotropic and homogeneous, lossy dielectric medium that has rho v is equal to 0, i.e. it means the charge free medium. And in these assumptions we will start our discussion. Now we will try to write the Maxwell equations in phasor form. That will help us a lot to find the propagation of the wave. Maxwell's equations in phasor form, and for that purpose, okay, just write first Maxwell equation, that is del dot D is equal to rho v, as it is charge free, so we can say 0, and in phasor form all the vector fields are termed differently by adding s. So now d is changes to ds in phasor form, and from here we have del dot E is equal to 0 as well, as epsilon is constant, and following this we can have in phasor form the change will occur here only. So this is the phasor form of Maxwell's first equation. There is no change except the notation. Similarly, the second equation's phasor form, just normal form, we have is equal to 0, monopole existence, and from here we can have phasor form of this equation. So this is the second Maxwell equations related to the existence of the monopole. The third one, that is related to the Faraday's law, that is minus del over del t with respect differentiation of b with respect to t. And if we transform it into phasor form, then this term del over del t can be written as j omega, and remaining terms will be as it is, just with the notation s. So in phasor form the modified equation will be minus j omega due to this, and b can be written as mu times h s. Hope it is okay. And the fourth equation, that is modified Ampere's law, that can be written as, the normal one is E plus epsilon E. Now in Maxwell's phasor form, these equations can be written as, this equation can be written as S is equal to the, it is nothing, just transform into phasor form Es plus epsilon remains as it is. Now this term will be j omega, and E will transform into phasor form. and after further little bit simplification, it will give us j omega epsilon Es. Omega is the frequency of the propagating wave. So in this way, we have the phasor form of the Maxwell's equation. Now we will try to solve these phasor forms and to find the wave propagation. So for that purpose, just start from the third equation, there various changes are reflected. So take the curl of equation 3, we can say, if it is equation 1, equation 2, then it is equation 3 and 4. So take the curl of equation 3, and from there we have curl means just cross product with the del. Curl of equation 3. This is mu Hs. Okay, curl means at both the sides of the equality it will follow. So curl of Es, sorry, it is Es is equal to the minus j omega mu curl of Hs. This is curl of E. So apply the property that curl of E can be written as del E minus del square E. This is left hand side, and right hand side can be written as it is minus j omega mu curl of del cross Hs. We have this relationship, and from equation first, according to the assumption, it is 0. So the remaining terms will be Es, and recall from unit 1, this is Laplacian, so keep in your mind, and minus j omega mu del cross the phasor form of H. We have this, and still we are finding that the relationship is between Es and Hs. That is not possible to solve it. So to bring the consistency, we can either bring this in E form or we can bring this in H form. So it is better to transform this, that we can put it from modified Ampere's law. We can write minus j omega mu, it will be sigma plus j omega epsilon Es, that is minus del square Es. This is the final phasor form of the phasor form that is simplified from Maxwell's equation. Now concentrate here. This is the permeability. For the material it is fixed. Conductivity, permittivity, all are fixed quantities. Frequency of any wave is fixed also. So what we can find, this is, okay, cancel it, minus minus. This is a constant term. So what we can write, del square Es is equal to this constant is represented by gamma square. Now we can write Laplacian of Es is equal to gamma square Es, where gamma is the propagation constant. It is termed as propagation constant. And further, if we simplify it, then we can say minus gamma square Es will be equal to the 0, and this is the second order differential equation. As it is Laplacian, it can be further written as in the direct with respect to del x square in Cartesian coordinate, del y square del z square is equal to the, okay, we can say is equal to the Es. And as gamma square we have is equal to the j omega mu sigma plus j omega epsilon. So gamma will be square root of this quantity, this full quantity here. And what we find there is, it is complex term. So gamma can be written as in terms of alpha plus j beta terms, where alpha is named as attenuation constant, and beta is named as phase constant. Okay, so in this way we have gamma and we have this equation. Now let us stop at this point. We will continue from this point tomorrow. Thank you.